We have proved this lemma using dependent random choice. We said that if you have a graph with at least epsilon n squared edges, then you can find the large set U, where the most of the delta sets inside of U have large common neighborhood. So this is stated that the only small fraction has small common neighborhood. From this, what we can show is the following theorem. Let's say epsilon is positive, and then delta is a natural number. And let G be again n vertex graph with epsilon n squared edges. And if H is a graph which is this many vertices, and moreover, let's assume that this is bipartite graph, with maximum degree and most delta, then G contains H as a subgraph. Okay, if this is true, then what we have? Then Ramsey number of HH is what? And most 8 times delta times 2 to the delta H, if delta of H and most delta. Why? If n is this, if you consider Kn, you color the edges of the Kn. And either red graph has more than half number of edges, or blue graph has more than half number of edges. So let's change this to 4. Let's write it 2 to the 2 delta. And one of the red graph or blue graph, satisfy this with the epsilon being 1/4. Once we have that, what? You apply this, then again, if H is bipartite, one more condition, then this guarantees a copy of H in your monochromatic graph, so you obtain monochromatic copy of H. So this is sufficient for our purpose. So let's say H is a bipartite graph with bipartition A and B. You have A and you have B. Similarly as before, we want to embed A into some set U in a way that the many vertices here has large common neighborhood. And then once you completed embedding A, you embed B one by one using this large neighborhood property. And of course, you have a boundary epsilon degree. And what? And by the previous lemma, there is set U with again, say at n prime be 1/8 delta times epsilon to the delta n. Then there are U with size at least 2n prime, such that less than this many sets satisfies this. So Most of them has a large common neighborhood. So certain sets are good and certain sets are not good. What's our goal? Our goal is if X has a neighborhood, say 3 neighbors, we want to make sure that their image here are good set. And what's the good set? So we call subset F of size delta good if its common neighborhood size is bigger than or equal to n prime. Okay? So we want to embed sets into, these vertices so that their image of neighbor of certain vertex is good. But that's not enough. If you have some vertex with a degree smaller than delta, then what would you do? So this definition, we only consider the set of size exactly delta. So we want to also consider its subsets. But our plan is to take embedding one by one. So instead of this 3 vertices maps to the good set, at the time we only embedded this above vertices, we only have embedded 2 vertices instead of 3 vertices. Third vertex is not yet there. So their image here is not complete. Then what do we want this image of this 2 vertex to be? We want it to be easily extended to any 3 sets that are good. For that, we want to consider the sets which is partially good, meaning that which is a set which is contained in many good sets. So that give us many choices for the third vertices. So we call it nice. We call a subset the S prime nice if it has size and most delta minus 1, and this S prime is contained in many good sets. But how do we measure many? So we use this expression. Delta minus S prime size fits many good sets. Okay? So you will see why we define it this way. Then what we have is we have the following property. If you have a smaller nice set, then there are many ways to extend it to a slightly bigger nice set. And nice set of size 1, in particular, if we have an empty set is good. Empty set is nice. Because what? If this is empty set, what does it become? It belongs to at least this many good sets, but the number of good sets is already that many from this expression. So 1 minus this times this is the number of good sets. So we have a nice set of size 0, and we will see that there are many ways to extend it to a nice set of size 1, and then there are many ways to extend to a nice set of size 2, and so on. The number of ways to grow a nice set into another nice set of size 1 more, that number give you the number of candidates for this vertex. Okay, then what we know is that for nice set S prime, there are at least 1 minus 1 or 2 delta U vertices U in U such that S prime union with U is also nice. Or it's good if it reaches the size of delta. Why? I mean, this is also not difficult. So you have this S prime and U. Then how many sets how many good set contains this? Okay, suppose this is not true, then there are what? Less than, say, I will not do the rigorous computation. Let's say you have some alpha, which is bigger than 1 over 2 delta, so that only okay, so let's say, so that there are this choice and this choice of the sets outside. So that okay, technically you have to subtract this size of S and size of S, but as I will not write in full detail, I mean, it's not too important. You will see the point. So this many choices lead to say nice sets, and this many choices lead to not nice set. And each of the nice sets, so if you extend it, then how many good set contains this? At most, what? Delta minus S minus 1 good set. So this counts the number of good sets that contains S prime and some vertex 1 more. And then here, what? You choose not nice set. So if you choose this, then this is not nice. So there are upper bound on the number of sets, number of good sets that contain both S prime and this one vertex. And then that's what? That's 1 minus 1 over 2 delta, and delta minus S prime minus 1 times this. Delta alpha is bigger than that, so if you just write it 1 over 2 delta here, and that only increase the total number. So what do you get? This is actually upper bound on the number of good sets containing S prime. But what does this? If you compute it, then this will be 1 minus 1 over 2 delta plus 1 over 2 delta minus 1 over 2 delta. Okay. Yeah. Technically, this is what? S prime, you have to subtract it. S prime, you have to subtract it. Then the number will match up, and then you will get this number. So the number of good sets containing S prime becomes strictly more than that. That's a contradiction that the S prime was nice set. Yeah, I wasn't gonna do the computation, but I pretty much did the computation, but you can do it again for yourself to check whether this is correct. So we know that. And also for every nice set, we know that the common neighborhood of F prime is at least N prime. Why? This is a subset. S prime is subset of certain good set S. And you have this, and then this already has size N prime because this is good. So this is also easy. Once we know that, now what? We now find the we first embed A to F, A to U. Injective function, F then maps A to U such that once you take a common neighborhood of Y, so you have A, then B, so you have Y, and its common neighborhood. And this four set, we want it to be mapped to nice set. This is nice or good for every Y in B. Once we do that, then for its Y, we know that the common neighborhood of the images of its neighbors, which is in G, their common neighborhood. If it's large, so we can embed Y into it. So that's our plan. So for this, we order this A into say x1, x2 to say x key. And then we embed one by one. So let Li be all the vertices which we already have embedded. So assume we have designate the image of x1 to xi, and assume we have defined f from Li to A, U, such that every partial neighborhood of Y, its image is either nice or good for all Y in B. Now what? Now we have to define and determine where we send x of I plus 1. So you have xi plus 1. It could have certain neighbors here, y1, y2, y3. And it could have some later neighbor, and then previous neighbor, and previous neighbor. Due to this, what do we have to do? We have to make sure that once you choose this, common neighborhood of this two that is large, meaning that this set is nice, and also this set is nice, which is a neighborhood of this, and also this set is nice. So we want to make the choice that those are nice. For each y, which is also the neighbor of this xi plus 1, we consider the set its neighborhood, which is already, whose image is already defined. We know that this is nice. That's what? This shows that there are many choices that extends this nice set into another nice set. But we have to make sure that we extend this set into a nice set, and then this set into a nice set, and this set into a nice set. So there are several sets that we need to extend it to the nice set by adding the common element. So we want that this together with this set is nice, this together this set is nice. So we consider all the candidates that extends this to a nice set, and all the candidates that extends this to a nice set, etc. Thus, by this implies that sorry. Yeah. There are at least how many? So there are this many good choice means that the number of bad choice is almost 1 over delta times u. So, and there are how many? Delta many choices of y. So number of bad choices is almost this. And then out of all good choice, you subtract it, and that's still good choice. So this many choices, the vertices w and u that satisfies that after you add this together with w is still nice or good for every y which is the neighbor of xi plus 1. And since this t is smaller than n prime, because what? We take n prime to be the number of vertices in H. So that means out of this many choices, at least one of them is not used yet. There exists a vertex W prime among those n prime vertices such that its W prime is not used yet. Then we just simply let we map it to a W prime. We repeat this. Then what? And for all y in B, what? The new set is also nice or good. Why? You have two cases where the y is neighbor of this, then by our choice, it is nice or good. If y is not the neighbor of this, and this is same as the previous one, and then this previous one is by induction hypothesis, it was already nice or good. So by repeating this, we have an injective function such that this is nice or good for each y. Then what? Now we order the vertices in B into y1 to y, say, t prime. Then for each yi, embed it into the common neighborhood of the image of its neighbor in such a way that yi is not embedded to the same vertex that's used before. It's possible because each of these that is nice or good, its common neighborhood that size at least n prime, and n prime is bigger than t prime. I mean, bigger than the size of H. So, it's shows what we want. Okay, so what we have proved, so from here we know that this is what? This is like 2 to the big O delta times size of, order of h. But we only prove it for bipartite graph. For non-bipartite, it's also known. Coulomb-Fox Sudakov proof is the most, best upper bound. They did it in 2012. They show that it's still slightly worse, but instead of delta, you have delta log delta, then it's upper bound holds. And indeed, so this is bipartite, this is non-bipartite. And then we can ask for lower bound. How small can this function be? The following theorem shows that it's not too far from the truth. So Graham, Roder, and Luchevsky proved the following. So there exists a constant C satisfying the following, that for every n bigger than delta, bigger than 1, there exists bipartite graph H with maximum degree than most delta, and its Ramsey number is at least 2 to the sum C times delta times H. It shows that in here, up to this constant, this is best possible. This is bipartite graph. And also for non-bipartite graph, again, we don't know whether this law can be omitted or not, but that's the best we can do. Even if, it could be or could not be. But anyways, these bounds are quite close to best possible in such a sense. Okay, so maybe so I will briefly describe how they prove this. So what they do is first you consider H as a m vertex, say delta regular graph, which is random regular. So you have set A and set B, then you choose here a regular, randomly a regular. How do you choose a random regular graph? So formally it's like this. So you consider all possible delta regular graph, and then you can list all of them and you choose one of the random. Yeah. But in analysis, lots of times, how do you do it is you consider this half edge. Then you consider 3 regular graph. You consider half edge, meaning that you have 3 vertices, 3 vertices here, 3 vertices here, 3, 3, 3. Now you have 9 vertices and 9 vertices. There you take a random perfect matching. Then, it could give you a multigraph, but you condition on the having not multigraph. You get a random 3 regular graph. That's how you can actually manual time analyze this. But anyway, so that was not the point. So you take this random regular graph. Because this is random regular, you can show that the edges are greatly distributed. Okay, now what you do is you have n, and then you have m, and then you have like, let's say this is n prime, and then n. So you have these three. You consider this m, smaller one. You consider km, complete graph on m vertices, and then you consider random coloring. So you have like red, green, red, green, red. And then what you do is you blow up each of the set into one vertex into many vertices, so that what you have n over m vertices, n over m vertices, n over m vertices, n over m vertices. So let's say your original graph was like colored in this way. And what? And you mimic this. So these are all blue, all red, all red, all red. Okay, so this is your coloring, and inside of that is arbitrary. See? You don't really care, arbitrary. Then what do you know? So this is also well distributed because this is random. For example, well distributed means that no matter you take a large set here, then there should be many edges between them. Yeah. So what kind of thing we can prove it here? These are well distributed. These are well distributed. And so, for example, what you can prove is this is well distributed. So that means that if you take say 1,000, I mean, so these are all very big number. I mean, this is much smaller than the other two, but they are all very big, like 10 to the 100 or something. What you can show is that if you take, say, 1 billion vertices and 1 billion vertices, and then you see the edges between them, then this is random coloring. Around half of them are red and around half of them are blue. So you can show that. Between two sets, X and Y, around, so let's put it this way, less than 0.51 fraction has the same color. So you know this. And now what? You have that, another one is that in this H, this is G. H is also quite random, meaning that if you divide H into parts, say 1 million parts, so again here, when I say 1 billion, this is a large number, but much smaller than any of this. Here again, you divide it into 1 billion parts, which is much smaller than any number of this, but still quite large number. Then what you can show is that, okay, you check whether there is H between these and these. H between these and these. Say A1 to A2 to AT, B1 to B2 to BT prime. Then at least say 0.6 times TT prime pairs out of that many pairs of AI and BJ contains an H. So you can show this. Because this is random graph, then the edges are well distributed. That means you divide it into finitely many pieces, then most of them that are containing edges, at least that many. But now what? If you have H in this coloring as a monochromatic coloring, then due to your choice, if you choose it quite well, then none of them fit into one part. So this is quite much larger than this, but much smaller than this. So they have to go to certain part. So this has to be in here, and then this has to be in here, and this has to be in here. And then this has to be, say, in here, this has to be in here, this has to be in here. Maybe this part and this part both goes to the same part, but I mean, it's not too important. So here I just said about partition, but we can even delete some parts and then remaining one, same thing holds. So in such a case, I mean, if one of them go to most of them here and a small go to here, then you forget the small parts. Anyway, what I want to say that is that if we have a monochromatic H in here, that gives you this set. So the vertices that map to here, you have it here at A1, and vertices you map to it here at A2 and A3 and B1, B2, B3, and so on. But let's say you have a red monochromatic H here, then what? Whenever there is an H between this, then that has to be mapped to red. So let's say this one is going to here and this one is going to here. And then if there is an edge between them in here, then this has to be red. And this has to be red. Due to how we choose it, if one edge is red, that means everything is red. And then this is red, right? Then what do we have? Then in here, at least 0.6 pairs contains an edge, meaning that that pair contains a red edge. So that pair contains a red edge. That means if you take this and this, between them, so they correspond to this vertex and they correspond to this vertex. This vertex and this vertex, at least 0.6 fraction of them has to be red edges. But we said that this is very distributed, so only 0.51 fraction have the same color. So it's a contradiction. So because this is very distributed, you should have a patch, you should have a part which is close to being monochromatic. But this is very distributed, though. Every part, it has a half red, half blue. Of course, I just said here like billion or million. So you have to choose it wise so that this is not too small. If this is too small, then you should be able to find the monochromatic one. So you should choose this number to be not too small and not too large. And then you have to optimize the constants, then you get this inequality. Anyway, so that's the rough idea on how you prove, how these people prove this. So this bound zone Ramsey number is close to being tight. Okay, there are survey by Colon, Box, Stockholm in 2015 about the crack Ramsey theory. So I recommend you to take a look at it. And also there is survey by Fox and Sudakov in 2011 about the survey about the dependent random choice. That's also good to look at it. And also there is a lecture note about Landis theory by Wigderson, Yuval Wigderson. That's also good to see more about the Landis theory. Okay, so we talked about some graph-Ramsey theory. So next time we will discuss some about hypergraph-Ramsey theory. Okay, yeah, thank you for listening. I will see you in next video then.